Well, thank you very much. It's a pleasure to be back in Korea. Okay, so the topic really is boundary amenability. So let me just start with basic definitions. So the motivation for the talk is that with Camille Orbez and Vincent Girardel, we proved that out Fn is boundary amenable. But I think most of the talk is going to be just about what boundary amenability is, how do you prove it for some simple groups, what are some of the strategies, and why would you want to? You know, why would you care about boundary amenability? That's the plan for the talk. If I get some time at the end, I'll tell you about out Fn as well. But that's sort of a secondary importance. Okay, so what are the definitions here? So we'll have a countable group. It doesn't have to be finitely generated, but maybe most of the time it will be. Countable group. And we have a topological space. And we have an action of gamma on X by homeomorphisms. So these are just topological. Okay, so we'll say that this action is topologically amenable. The action is topologically amenable if there is a sequence mu n. So these are going to be continuous functions that go from X to the space of probability measures on gamma. Okay, so I'll denote this by prob gamma. Okay, so you should think of this as being just an assignment of a number to of non-negative number to every element of gamma, and they add up to 1. So this is a subset of, if you want, of L1 of gamma. And it has the induced topology from L1 of gamma. And this topology is really the same as topology of pointwise convergence. Okay, so this is the space of probability measures on gamma. Okay, so I want a sequence of continuous functions which are asymptotically equivariant. Okay, so most naively you could ask for an equivariant function because gamma, of course, acts on X and it acts on the space of probability measures. And so naively you might say, well, maybe, but that turns out to be too strong. So you just want asymptotic equivariance. So what that means is that for every gamma in gamma, if I look at the sup over all X in X of the norm of say mu n of gamma X minus gamma mu n of X. Okay, so this would be 0. This is the L1 norm. This would be 0 if gamma was equivariant on the nose. But I just want this to go to 0, to converge to 0 as n goes to infinity. Right? So as n grows, this is getting more and more equivariant somehow. Okay? And then the group is boundary amenable. Gamma is boundary amenable if gamma admits a topological amenable action on a compact Hausdorff space. Okay. Okay, so some quick examples. So let's take the group Z plus Z. Okay, so Z plus Z is acting on its own Cayley graph, for example. So I can visualize it like this. Z plus Z. And what I claim is that the action of gamma on a point is topologically amenable, and therefore gamma is boundary amenable. Okay, so I claim that gamma acting on a point is topologically amenable. Okay, so how do I prove that? Well, you see, these functions are really just individual measures because x is a point. So I just need one measure. Mu n is just going to be a single measure. And I want this measure to be evenly distributed on some large square. So I'm going to take, here's a square, which is minus n squared. So take that square inside the Cayley graph and equidistribute the measure mu n on all the points inside the square, right? So you count how many points there are. It's roughly n squared, and then or 2n plus 1 squared, and then you assign 1 over that number to each point inside the square. So mu n is just going to be equidistributed on this square. Okay. And now, what does this amount to saying? How do we prove this statement? Well, if you think about, so you're fixing an element of the group. So, for example, you can think of it as being a generator. It doesn't have to be. It can be anything you want. But then, how do you picture this difference? Well, you are going to have the original square, and then you're going to have a translated square, right, by gamma. They look kind of like this, where gamma is a fixed translation. The squares are growing, right? They're getting bigger and bigger, and gamma is a fixed element. So the amount of the number of points that are in the symmetric difference is going to be, the percentage of these points is going to 0, compared to the number of points inside the whole square. And so, this difference is going to be non-zero only on the points in the symmetric difference, but you're equidistributing, so you're dividing by the number of points in the whole square, so this will be going to 0. Okay? And so more generally, you can prove that if gamma is an amenable group, so what we used here is just the fact that there are Follner tiles. So these are called Follner tiles. They're big subsets of the group where the number of points on the boundary is proportionally it's going to 0. The proportion is going to 0 compared to the number of points in the whole tile. Okay, so what this argument really shows is that if gamma is amenable, then it is boundary amenable. In fact, gamma, the action on the point is topologically amenable. Okay, so that wouldn't be too interesting if that was the only kind of example. But the point is that there are groups that are not amenable, and they still admit amenable actions on interesting spaces. So the second example is going to be a free group. Okay, so the Cayley graph here looks like a tree. It is a tree. It doesn't just look like a tree, but it looks like it. Okay, and then there's a natural space that might be suggested by the terminology, boundary amenable. So you look. So you should look at, to find candidate spaces, you should look at the boundary of the group. And so here, the boundary is the Cantor set at infinity. So I want to take X to be F2, which is the Cantor set. And you should think of it as a space of, a point in this Cantor set is given by a ray that starts at 1, or equivalently, it's an infinite word in the generators. Okay, so I claim that the action of gamma on the boundary, or let's just say F2 here, on the boundary of F2 is topologically amenable. Okay, so how do you see that? So I take a point in the boundary, right? I have to give you a function mu n that goes from this Cantor set to the probability measures on this free group. So you give me some point at infinity. Here's x. And what I want to do is draw my ray that goes from 1, right? That somehow goes all the way to this point x. And then for mu n, I count off the first n points along this ray, and I equidistribute the measure on these n points. Okay, so you'll have measure 1 over n concentrated on the first n points along this ray. So mu n of x, this is equidistributed on the first n points of the ray that starts at 1 and goes to x. X is at infinity, so it's an infinite ray like this. And then how do you prove the statement? So it's again proof by a picture, which now looks like this. I have so there's 1, there's x over here. Well, let's look at gamma x. I guess we have to look at mu n of gamma x. So I have this ray that goes from 1 to gamma x, and then I also have a translated ray between 1. I start with the ray from 1 to x, but I hit it with gamma. So this will now go from gamma to gamma x, right? So there's some point gamma here, a vertex in this tree, and then I go to the same point at infinity. So the rays are eventually going to merge into one ray. This will be the picture, right? And then I'm for mu n, I'm measuring off the first n points along this ray, and the symmetric difference. It's working. Okay, so the symmetric difference is going to be concentrated here and here, but that's some fixed number of points that depends only on gamma and x and only on gamma. I mean, the distance between 1 and gamma is some fixed number. So the total number of points that you see in the symmetric difference in this part is going to be bounded depending only on gamma. And then you'll have some kind of part of the symmetric difference that will live way over here, right? So you'll have one ray, one segment of length n that goes like this, and the other segment of length n that goes like this. And they might not stop at the same point, depending on how many points there are. But anyway, this distance here is always bounded. So it's kind of like in the picture over here, where the symmetric difference is small compared to the support of these measures. And so again, we see that this goes to 0. Okay. So this is in a way how you're supposed to think about boundary amenability. You have this group, and there's some sort of space at infinity, and what's going to make the group boundary amenable is this picture that you can go from the identity in the group to this point in infinity, and maybe the ray is not going to be the unique way to go to infinity. Maybe there's going to be some sort of ambiguity, but you should have some kind of a polynomially growing space. Maybe that will become clearer later. Some kind of polynomially growing space of ways of going to infinity, and so that if you change a base point like this, these different ways of going to infinity eventually merge into one. Okay, so that's somehow loosely speaking what boundary amenability is about. Okay, let me now say what's known and then why you would care about boundary amenability, or at least why I care, and about other people. But okay, so let me just say what's known about say inheritance. Like if you know a group is boundary amenable, then what other groups are boundary amenable? So okay, so subgroups. This is almost immediate from the definition that if you have a boundary amenable group, then any subgroup of it, any old subgroup, doesn't have to be finitely generated, it's going to be boundary amenable, basically by restricting the action. You can also go up, finite index. So finite index supergroups. Then extensions. That is, if you have a short exact sequence and both the kernel and the quotient are boundary amenable, then so is the group in the middle. There's a theorem of Adams. Maybe that was the first non-trivial theorem in the subject in the 90s, that hyperbolic groups are boundary amenable. So this was modeled really on this proof of free group. where the Cayley graph is now not a tree anymore, it's only delta hyperbolic, and you don't have a single ray, you kind of have some kind of a fuzzy ray. You have to talk about two delta neighborhoods of things. And so you have to be a lot more careful how you define this, but anyway, that was the subject of this paper. So all hyperbolic groups are boundary amenable. The action on their Gromov boundaries is topological amenable. And then this was later extended to certain kinds of relatively hyperbolic groups. A big theorem was proved by Günther, Higson, and Weinberger. Linear groups are boundary amenable. That is, any countable subgroup. So if gamma is a countable subgroup of so let's say GLNC. This also works for other kinds of fields, but let's just for simplicity say this. Those are boundary amenable. Then there are groups acting geometrically on cat0 cube complexes. On cat0 cube complexes. And then there is a theorem of Kida and independently Hammenstadt. Mapping class groups. And for us this is very important because our FN is very much like mapping class groups. So in fact our proof for our FN is going to sort of follow the strategy that Kida adopted. So let me then state the theorem, which is that out FN is boundary amenable. One can also use a similar strategy to prove things like out of a right-angled Arden group is boundary amenable, and various other automorphism groups. But this is somehow the guts of it. I mean, for the free group, the free group is the hardest right-angled Arden group somehow. There's lots of automorphisms. Okay, so let me now tell you about why I care about this. Okay, so the reason I care is that it implies something called the Novikov conjecture. And this is one of these things that people always say in talks but never explain what it is, and that's because it's not easy to explain. But maybe I'll try to say something about it. So the reason I don't know. So if gamma is boundary amenable, then this implies that Novikov conjecture holds for gamma. Okay, so what is the Novikov conjecture? Novikov conjecture. So this is a conjecture in the topology of manifolds. In manifold theory, the main problem is to classify manifolds. You want to, more specifically, given the manifold, say a closed oriented manifold, you want to give a list of all manifolds homotopy equivalent to it, up to homeomorphism. Okay, and there's the whole sequence of conjectures, maybe that culminates in something called the Farrell-Jones conjecture. That if you know the Farrell-Jones conjecture for the fundamental group of the manifold you're interested in, then you can, in principle, write down such a list. Okay, the Novikov conjecture is a weaker version of this Farrell-Jones conjecture. But let me try to say what it is. Okay, there's a fancy version of this when you say, there's some map called the assembly map, and then The Farrell-Jones conjecture says it's an isomorphism. The Novikov conjecture says it's rationally injective. Okay, so but that doesn't really help very much if unless you're really into it. So let me try to say it differently. Okay, so the Novikov conjecture can be stated for a group, right? So for any group, you can make the Novikov conjecture for that group. Okay, so the Novikov conjecture for gamma. So what does it say? Okay, so let H from M to N be a homotopy equivalence between two closed oriented manifolds with the fundamental group. So of course they have the same fundamental group, and I want the fundamental group to be gamma. Okay, then M and N have the same certain invariants called higher signatures. They have the same higher signatures, and I'll explain what they are. Okay, so first of all, the signature. What is a signature? So if you have a manifold whose dimension is divisible by 4, you can look at the intersection pairing in the middle dimension. That's symmetric, and you can diagonalize it. You can find the basis so that the intersection pairing is represented by a diagonal matrix. And then you count the number of plus signs and the number of minus signs, and the difference is the signature. Okay? So the signature makes sense for manifolds divisible whose dimension is divisible by 4. Higher signatures are, so let me give you an example of so let's say M has dimension 4n plus 1, and its fundamental group is Z. Okay, then there is a higher signature that's associated with them. It's some number, and then the conjecture, which is by the way known for Z, because for example Z is boundary amenable because it's amenable. Okay, so homotopy equivalent, such manifolds are going to have the same higher signature. Okay, so what do I do? How do I extract this higher signature? So I make a map to the circle that's a pi1 isomorphism, right? This circle is a classifying space, if you will, for the group Z. So I can find a map like this that's a pi1 isomorphism. And then let's say M is a smooth manifold. This is all for topological manifolds, but you can just to simplify the discussion, imagine that M is smooth. Then I can make this map smooth as well, and I can take a regular value and I can pull it back, right? So the picture is something like this. I have this manifold M, and there is a map to the circle, and I take a regular value of this map and I pull it back, and I get some codimension 1 submanifold, which now is going to have dimension 4n. So this is F inverse of X. Its dimension is 4n. I can take its signature, and that's an example of a higher signature. Okay, so the signature of F inverse of X is the higher signature in this case of M. And the conjecture predicts that whatever you compute here is going to be independent of the manifold. It only depends on the homotopy type. So maybe you can guess what the general definition of a higher signature is. If the group is something else, you can always map the manifold to K gamma 1. So, there's a classifying map to the Eilenberg-MacLane space for that group. And then you can take a cohomology class. Like here, this point really represents the first cohomology class of the circle. So you can take a cohomology class in the classifying space. You can pull it back, and with luck, you can represent it by a submanifold. So if you don't have, this is one of these things where things become technical, but you can even if you cannot represent this cohomology class as a submanifold, it turns out the signature makes sense as long as the formal dimension is divisible by 4. If the Poincaré dual is a homology class of dimension divisible by 4, the signature still makes sense. Okay, And so this is how you define it. And that's the Novikov conjecture. And so if you want to, you have your favorite group that you'd like to prove the Novikov conjecture for, then you could hope to embed it into one of the groups for which let's say boundary amenability is known, because it passes to subgroups. So if your group is linear, then you're done, because you can cite the theorem. If it's not linear, but maybe it embeds into the mapping class group or out Fn, then you're happy too. So that's why I kind of like this. And I keep thinking about these more general conjectures, like the Farrell-Jones conjecture, for example, is still open for out Fn.
So the conjecture is that the Novikov conjecture holds for all groups?
Novikov conjecture holds for all groups. That's the conjecture. There are no counterexamples to that. But it's not, it's only known in some kind of, for groups where geometric group theory can make some, where you have something to work with, something geometric. Okay, so now let me talk about how one goes about proving boundary amenability for groups that are maybe a little more complicated than free groups. I should say that boundary amenability is known to fail for some groups. It's not. There are groups that are not boundary amenable. So you may have to find a different strategy to prove the Novikov conjecture for some groups. Okay, so the main technical kind of input into what's coming is a lemma that's due to Ozawa. So I'm going to state it and maybe make some comments. So Ozawa's lemma. This really simplifies a lot of, if you just try to use the definition, then you run into all kinds of issues. But Ozawa's lemma simplifies a lot of it. Okay, so here we have a group acting on something compact. And we also have the same group acting on some countable set. Okay, so in the definition, this countable set is the same as gamma. It's acting on itself. But here we are allowing more general countable sets. For example, stabilizers could be non-trivial. They don't have to be. Okay, so and then just like in the definition, we'll have these mu n's that go from x to the probability measures, but not on gamma, now on k. Okay. So that's some extra flexibility here. And these functions don't have to be continuous. They just have to be Borel. Right? So Borel means that, for example, I take an open set here, take its preimage. It doesn't have to be open. It just has to be in the sigma algebra generated by open sets. So that's much easier. Somehow, unless you're using the axiom of choice or something, basically anything you write down is going to be Borel. So you usually don't have to worry about this. And then there's no soup anymore. So for every x in x separately, no soup over x. And for every gamma in gamma, you want to know that this difference. I don't know, I wrote it backwards this time. Why? It goes to 0. Right? It's not soup anymore. So for every x separately. And you also want to know that the stabilizer of each point in K is boundary amenable. Okay, so there's going to be some sort of induction. If you have a class of groups, then you're going to be inducting on complexity. So the stabilizer of little k is boundary amenable for every k in K. Okay, then gamma is boundary amenable. The action on X may not be topologically amenable. There is a different space on which the action is topological. Basically, you have to do some blowing up. If you have an action where a point stabilizer is not amenable, then there is no chance that the action of that group on the space is topologically amenable, just by kind of restrictions. If you restrict to a point, you would get that the stabilizer point acts amenably on that point, but that's equivalent to being amenable. So it's not true, the action on X itself is going to be boundary amenable, but there is a different space, so kind of a more complicated space. Okay. Okay, so to illustrate this, let me prove that. So the example is going to be that I'm going to take gamma is PSL2Z, right? And PSL2Z is acting on the circle at infinity in the hyperbolic plane, right? So it's acting on the hyperbolic plane. It's also acting on the circle at infinity. I'm going to prove that this is. Well, that this satisfies Ozawa's lemma. In fact, here, point stabilizers are amenable. They're Z at worst, right? They're trivial in Z. And so here, in fact, this action is already topologically amenable. You don't have to do any blowing up. But let's just prove that this satisfies Ozawa's lemma. I have to tell you what K is as well. Okay, so the picture is I have this circle, and then of course whenever I talk about PSL2Z, I have to draw the Fairy graph. Right, so there's the Fairy graph, which, with luck, I will stop drawing at some point. And a K is going to be the set of vertices union, the joint union, the set of edges of the Fairy graph. So K is vertices disjoint union edges of the Fairy graph. See, if I just used edges, then this would essentially, the action on the set of edges is free. So this would be essentially the group itself. In other words, I wouldn't really be using Ozawa's lemma very much. But since I'm throwing in vertices and the action of the vertices is not free, right? The stabilizer of a vertex is Z. Then I'm actually buying myself something. It's easier to argue this than just considering the set of edges. Okay. Okay. So now I have to define these maps. I have to go from mu n that goes from X into the probability measures on K. Okay, so there are two cases depending on whether my point on the circle is rational or irrational. So if X is rational, in other words, if it coincides with the vertex of the Fairy graph, then I know where to send it because I have a vertex in K. I can just take the measure that's supported on that vertex, right? Then define mu n of X to be, well, I'll write it like this: delta X. This is the Dirac mass, or whatever it's called, for just a measure supported on X. Okay, so I wouldn't be able to do this if I was just considering, K to be gamma. I wouldn't have X in my space, right? The stabilizer is Z there. It's not a free orbit. And notice that this doesn't depend on n, but that's because this is actually equivariant on the nodes, right? This is just both sides here you're taking gamma times delta X, and this is also gamma times delta X. So I don't have to argue here at all. And also notice that these functions that I'm going to write down are definitely not going to be continuous because I'm distinguishing cases, rational and irrational. Okay. So now, what happens if X in S1 is irrational? Okay, so then I'm going to use the idea from the free group, and you could say that's cheating. I mean, of course, PSL2Z is just a finite extension of a free group, so we already know it for this group. But it's the method of proof that matters here. Okay, so if I have some point, say X, that's irrational on the circle, what I want to do is I'm going to choose some base point once and for all, kind of in the middle of the hyperbolic plane. And I'm going to look at the edges separating the base point from x. So I have this one, and then this one, and this one, and so on. And I'm going to concentrate mu n on the first n of these edges and equidistribute them, right? So probability 1 over n on each of them. So mu n define mu n of x to be equidistributed on the first n edges, separating the base point from x. And then this fact is shown in the same way as for trees. Okay, but it's important to maybe pause and say that this space is hyperbolic. The Theory graph is hyperbolic. So I could say, well, we already know how to handle hyperbolic spaces. We can just look at Adams and do whatever he does. And this really, morally, this is the same thing. But the thing you have to be careful is that this graph is not locally finite. So when you take a delta neighborhood of some rate that goes to infinity, that's going to be locally infinite set. You won't be able to say, well, go distance n and take all these points in the delta neighborhood and equidistribute the measure, because there are infinitely many points. I don't know how to equidistribute the measure on an infinite set. But somehow miraculously, the geometry of the Theory graph is such that if you don't take the delta neighborhood and then say the equidistribute there, you take all points that happen to live on some geodesic from the base point to the point in infinity. That set is going to be locally finite. Okay? Even though, if you just think about delta neighborhoods, that's local infinite. But not all those points live on the geodesic from the base point to this point in infinity. So there's some kind of local finiteness that holds, even though the graph itself is not locally finite. Okay, and that's somehow what's being used here. So that's going to be an issue in our case. We'll also have some kind of a hyperbolic space, but we won't know things like this. This is kind of the main technical issue that we have to face. All right. Right. Yeah, and maybe I should point out another fact. The Gromov boundary of this of the Theory graph is exactly the set of irrational points in the circle, and that's also somehow underlying this argument. Given a point irrational point on the circle, you can think of it as being a point in the Gromov boundary, and so you can start drawing these rays, geodesic rays, from a point in the Theory graph to that point at infinity. All right. So let me now talk about Kida's proof for mapping class groups. Unless there are questions, you should feel free to ask questions. Yeah. Okay, so Kida's proof for mapping class groups. It basically follows these lines. This is going to be an elaboration of this example. Kida's proof for mapping class groups. Okay, so the idea is to argue by induction on the complexity of the surface. Okay, so it's induction on the complexity of the surface. And then there is this little dictionary chart. So, maybe I'll start. So PSL2Z, which you should think of as being basically a mapping class group of a punctured torus, right? That's one of the simplest mapping class groups. And over here, it's the mapping class group of an arbitrary surface. And so here we had a hyperbolic plane. That was the picture we drew over here. And then over here, we, of course, have Teichmüller space. And then over here we had the circle at infinity, and And over here we'll have the boundary of Teichmüller space, which is Thurston's space PML, projectivized measured laminations. And then and then we had irrational points on the circle. Okay, so those are somehow generic points on the circle, right? Those are rational points are sort of boring. Anyway, irrational points. So over here we have irrational laminations. By this I mean those that fill. In other words, the complementary components are disks and once punctured disks. And then over here we had the theory graph, and then on this side we have the curve graph, or the curve complex. Okay, and so now we want to say the same words using this side of the dictionary, and see where we get into trouble. Right, that's the basic strategy. And what I want to do is take, so X is going to be, so I want to plug it into Zawa's lemma, right? So I need X and I need K. So X is going to be PML. I have to do this because I'm looking at this argument here, and X was the circle, but I didn't write it down. But anyway, this was X. So now I take PML. Now notice that here there are points whose stabilizer is big, right? If I just take a single curve, the stabilizer of that curve is some slightly smaller mapping class group, but still not amenable. And so the action on PML is not going to be topologically amenable, but it will satisfy Zawa's lemma with the clever choice of K. And what is K? K is going to be the vertices of the. I mean, I didn't really need the edges here. This was just to make the discussion simpler. But the main thing was vertices. So K is going to be the vertices of the curve graph. Okay, and then I somehow know this because the stabilizer of a curve is some kind of a simpler mapping class group. So by induction, you know that that's boundary amenable. And then I need these functions mu n, and mu n is easy to define if the lamination is not irrational. Okay, so if I by analogy with this, if I have a rational number, then I just define it to be that. So if lambda is not irrational, well, what does the lamination look like if it's not irrational? Well, it could be that it has a curve as a leaf, and it could also have maybe an irrational component that's supported on the subsurface like this, and the support of the subsurface is here's the subsurface. So maybe this curve doesn't have to be a leaf, but it's just a boundary component of the subsurface. But in any case, the point is that every non-irrational lamination has a canonical finite set of curves that's associated to it. Namely, those that are leaves and those that are boundary components of subsurfaces carrying components. Okay, so then there is then define mu n, and this is again going to be independent of n. This is just a characteristic set of curves. So this is the closed leaves and boundary components of supporting subsurfaces. Okay, so this is non-empty when lambda is not irrational. If lambda is irrational, this set would be empty. So you wouldn't be able to define it this way. But this doesn't depend on n, and the assignment is equivariant. So there's nothing to prove here.
Distribution and then
Oh yes, 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 yes. I forgot. This is just a set. So so this is equidistributed. So equidistributed on this set. Right. Thanks. Right. It's important that that's a finite set, so that I can equidistribute. Now, what do you do when it's irrational? Well, let's see. Where did my eraser? There it is. What do you do when it's irrational? So then you want to use atoms. Really, you want to say, well, the curve complex is hyperbolic, and so I can run atoms on the curve complex. Okay, so if okay, so maybe I'll state. So this is one ingredient somehow, the fact that you can assign this canonical collection of curves to every non-irrational lamination. But there are maybe a couple more things. So two more facts before I define mu n. So the first one is that the Gromov boundary of K, or of the curve complex, of the curve graph. This is a theorem of Clarke. Is, well, secretly it's the quotient of, but maybe don't focus on that too much. The quotient of the space of irrational laminations. Just like in the case of the Ferri graph, right? The boundary, the Gromov boundary of the Ferri graph is exactly equal to the irrational points on the circle. And the same thing holds here, except you have to take the quotient of this space. It's not one-to-one. You have to forget the measure, right? They're non-uniquely ergodic laminations, and if you put different measures on the lamination like this, it'll represent the same point in the Gromov boundary, even though the measures are different. So that's why it's a quotient of that. But that doesn't matter very much. The point is that you can define mu n of x to be. So this x is of course some equivalence class of let's see, mu n of lambda. Okay, so lambda here is irrational. It's an irrational lamination. So I can view this irrational lamination as sitting on the boundary of the curve complex, and so I can use atoms. So this should be so equidistributed. So I'm going to put it in quotes because you have to. There's some work that needs to be done here. Equidistributed on one or take some base point alpha. Alpha is my base vertex in the curve complex C, which is K really. I called it K. K is a set of vertices. Okay, so alpha lambda. So lambda is sitting at infinity. So I can think about the ray that goes from the base point to lambda. I can think about the first n points on the first n points. N points of.
It depends on the choice of ray.
On the choice of
ray. Ray is not unique.
The ray is not unique. That's why this is all in quotes. Yes. So right. So in Adam's work, it's also not unique, but there is some local finiteness. And here, the necessary local finiteness comes from the second fact about tight geodesics. Tight geodesics in the curve graph. So that's those are special geodesics. So typically, 2 points in the curve graph are going to be joined by infinitely many different geodesics. But there are geodesics that are better than others, and those are called tight geodesics. So this is a concept from Mazur and Minsky, who also proved the hyperbolicity of the curve complex here. And that set of geodesics has local finiteness properties that are required here. So if you do the, Adams proof in hyperbolic groups, you can translate that proof into this setting but every time you say geodesic, you now put the word tight in front. Okay, so it's and then Adams's proof works. So this has local finiteness. So this was this local finiteness that's necessary was proved by Bowditch some time ago. So there's local finiteness properties needed for Adams's proof. Okay, so I won't precisely say what mu n of lambda is, but it's the same formula as appears in Adams, except that you have to put the word tight in front of geodesics. Okay, so these are the ingredients in Kita's proof. Now, what we do, maybe in the last few minutes, I'll say a few words about. Maybe I should pause and ask for questions. Okay, so yes.
So what did you write again? So
Here?
Corresponding the irrational points of Bestvina in the vector group of sigma.
The irrational points on the circle correspond to these irrational laminations. Laminations. Sorry. Okay. So let me then try to extend this dictionary to out Fn. And this is going to be our starting point. So the analog of Teichmuller space is Cauchy-Voigtmann's outer space. It's not a manifold, but it's some kind of a contractible space where out Fn acts properly. Then this space has a natural compactification. So I guess this is called CVN, and then there's a natural space at infinity, and a point in here is represented by an R3, by an action of the free group on an R3, which you can think of as being the dual to a lamination. If you have a measured lamination on the surface, you can take the universal cover, and you can take the dual object, which is going to be an R3. And here you don't have there's no place to draw the lamination, but you still have the dual R3. Okay, so a point in here is an R3. And then, not surprisingly, there are R3s that are considered to be irrational. Irrational R3s.
Quick question.
Yes.
In the case for the mapping class group, so secretly you're proving that it's topologically amenable on the action and the boundary of curve complex, right? Not the boundary of the time space.
Well, no. You have to. So first of all, for boundary amenability, we need a compact space, and boundary of the curve complex is not going to be compact. It is true that the action on the boundary of the curve complex is topologically amenable, but that's not compact, so that's not enough. What really happens in Ozawa's lemma is that you have to enlarge the space. I mean, I think of it as blowing up or something. I mean, it's not going to be x, but some kind of a product of x and spaces. Whenever this thing here is not amenable but only boundary amenable, then it acts on some compact space, and you're going to basically take the product of x with that compact space to make sure that these stabilizers act amenably. So it's yeah. You always have to go through this lemma. Okay. Right. Okay, and then the analog of the curve complex is the complex of free factors. Okay, so you should think of a free factor as being really analogous to a subsurface. But if you have a curve on a surface, right, then it determines some subsurface. I mean, maybe it determines two of them, but roughly speaking, it's kind of the same thing. The only difference, so if you have a subsurface, then there is a well defined complementary subsurface, and with free groups that's not the case. You have a free factor. There are many different complementary free factors, and that's somehow the one of the issues in OutFN, that you know this leads to another complex, namely the complex of free splittings. This is when you choose the complementary factor that's really a free splitting, and the complex of free splittings is also hyperbolic, but it's very different from this one. We know this one is hyperbolic. This was so Mark Fain and I proved this some time ago. We also know what its boundary is. The boundary is a quotient of the space of A rational R3s. This was proved independently by Hammenstadt and by Patrick Reynolds and myself. So some of these basic ingredients are all in place. The main difficulty is, well, there are two really. Two main difficulties. One is that so we want to induct on the complexity again, just like Hida, but now the stabilizer of a. So what are the difficulties? If I look at the stabilizer of a free factor, right? So our space K is going to be, our countable set K is going to be the space of free factors. So I look at the space of, I look at the stabilizer of a free factor. Well, that's going to be something like, this is what we call something like OutFN A. These are automorphisms of the free group that preserve A. Well, that doesn't split as some kind of a product of simpler OutFNs, right? So here the stabilizer of a curve is basically the product of simpler mapping class groups, and that's not the case here. This group doesn't necessarily split. It's not, So what we have to do is really prove simultaneously for not just OutFN but also groups like this, where in fact A is replaced by some kind of a collection of free factors. So we have to inductively prove for groups like this, like that one, even slightly more complicated. Okay, so that's one point. Another point is that there are no tight geodesics, or at least no known tight geodesics. Nobody has been able to find some kind of a class of geodesics that behaves in a locally finite manner. So what we really have to do is work in outer space is locally finite, and so we really work in outer space, and then we find some geodesics there, and then we project those to these complexes, and that's how we get local finiteness. Now, unfortunately, when you get to these relative versions, they have their own outer spaces. These relative outer spaces, we have to consider those, but those turn out not to be locally finite. They're locally infinite, and so then so at some point one has to get lucky, right? Otherwise, you don't prove the theorem. And somehow somehow the lucky thing for us is that these paths that we construct, these geodesics, they're basically folding paths, if you know the terminology in OutFN. They just happen to have finiteness properties that are needed here, even though the spaces where they live are not locally finite. But they somehow, we get lucky enough that this works. Okay, so I think this is a good time to stop before getting into too many technicalities. So thank you very much for listening.